Hello everyone and welcome back to my channel. This video is it's essentially the part 2 of building a mental model to understand performance. This episode is more on the sort of the hardware level. I sort of hinted in at the end of the part 1 that it's important to understand the hardware on which your applications are running so that you can become a better programmer. And I believe that. However, it is hardware centric. If you don't have an interest in that, then this is not the video for you. That's not to say that I'm going to go deep into the electronics part, but conceptually I want people to understand, as a programmer, having a good understanding of modern CPU architecture is very beneficial. You may not be able to use it every once in a while. Maybe you can't use some of it in C#, you may be able to use it in C++, but the concepts are important, and there are many things you could be doing in your C# programs as well, where you may be able to benefit or take advantage of what you learn here today. Today we're going to be looking at instructions, pipelines, CPU caches, prefetcher, branch prediction, and maybe registers. I'm not sure if we have the time. So, or maybe make another video on that. They're not as important, or they're of course they're important, but they're not part of the kind of the basic topic I'm trying to talk about today, even though registers are also at the hardware level. All right, so before we proceed, I want to show you this slide. Now the data here was compiled by Jeff Dean. He's a fellow at Microsoft, and he did it many years ago, maybe 6, 7, 8 years ago. So some of the data is a bit outdated, not that much has changed in that regard. But what I'm trying to emphasize here is most of our applications have issues at a different level. Today's applications are accessing services, external services. By external, I mean external to the application. They're using asynchronous programming, as in they're using message queues or message brokers to assist with the kind of the decoupling of this application with other applications. They of course are using databases and such. The biggest performance issue is really network related. So network I/O is the slowest of all things we could possibly be doing in computers today. So the more network calls you make, the more data you send and receive from the network, the slower your application is going to get. In my applications, I strive for, and most times I will succeed in this, for every one request that comes into my application, that one request should have sort of populated a page on, let's say, for a user, and that in that one request, I will only ever make one call to a service and one call to a database, meaning let's consider services and databases to be the same in terms of network calls, and I'm talking to 4 services. I will potentially try and make those calls to those services in parallel or concurrently, if that's feasible, which most of the time it is, because no one service is dependent on another service. And in that one request to all services, so if I've got 4 services, I'm making 4 calls to the services, but there's only one call per service, and they're all happening at the same time. So I'm sort of waiting for the service call that takes the longest, rather than doing them sequentially. And that's how I program. At no time are you allowed, let's say, to make multiple calls to a database or multiple calls to a service for the same request that comes in, right? So if you strive for that, then you'll be a lot better off. Now I understand it's hard, it's not the easiest thing to do, and it sort of goes against the grain for many people about best practices, and maybe your framework doesn't support this, that, and the other. For me, that is more important, and that's what I would do. Depending on the application, maybe it doesn't matter to you. But then this talk won't matter to you either, because this is way beyond. If you're talking about seconds in the network I/O realm, here we're talking about nanoseconds, microseconds, milliseconds. Right? So if your issues at the seconds level, this is not where you're going to get that information as to how to improve performance. But nonetheless, it's important, and there are things you can be doing as a C# programmer to improve your the performance of your code, but when you're having issues dealing at the milli, micro, and nanoseconds. All right. So the interesting part here in this chart is that the L1 cache, and I'll talk about L1 and L2 and this sort of thing, but the L1 cache takes about half a nanosecond. Now light, the speed of light is 186,000 miles a second. Light can travel 1 foot, so that's 10 inches. So 1 foot is about here. 1 foot in a nanosecond. This may not make a difference to most people. Okay, so that's a foot, but it does make a difference in that. And there are some real world scenarios, where I've had a situation where the servers to the main application were co-located in the same building, but this was like a 20-story building, and the servers being in the basement while the offices were on the top floor actually made a difference to our business, as in the application that we were building. And so we actually had to bring the servers up to the top floors to get that performance difference that we were getting, because of the fact that they were at a large distance away from the usage. Specialized application, very critical, but it's not a normal application, and it was not a normal business application, but that matters. Now, when you look at the diagram for L1 cache, L2 cache, and L3 cache, you'll realize that these caches are on the same chip. So if you have a CPU chip, let's say that my palm is the chip on which your CPU core is, then the CPU core is occupying some space on that silicon. And L1, L2, and if there's an L3 cache, not all CPUs have an L3 or maybe even an L2 cache, they're all on the same silicon in the same chip. It's not like they're somewhere on the motherboard. They're on the same chip. And the difference between, you can see here, between accessing something in L1 cache versus accessing something in L2 cache, that's 14 times slower. That little microns apart is making a difference in the time it takes to get data from either L1 or L2 or L3, right? So you have to understand that the physical distances actually are making the difference. So the closer your caches are to the CPU cores, the faster your applications can run. Of course, that's just at a high level. There's many things that can go wrong or that need to be in place for the CPU to go at full clip. But I want to ask you to look at the distances, or say the differences in the network access. So sending a packet from California to the Netherlands, the last line there, that takes 150 milliseconds. Now I'm guessing that was done on a very fat pipe, being Google. You're already on the kind of the backbone, OC38 or whatever backbone, the internet. So it's not like you're using the kind of network access that we have typically at our homes and offices. We're not sitting on those fat backbones. But let's say it's 150 milliseconds. That's 150 milliseconds. That's 150 million nanoseconds slower. Not slower, but that's how much time it takes. Now somebody else on the internet changed the numbers there to where if the access to L1 cache were a second, and then so what would the rest of the numbers fall in? And you can see that if accessing L1 cache were a second, then accessing L2 cache would be 14 seconds. Accessing main memory would be 3 minutes. And the main memory is a physically separate chip on the motherboard. So it's not on the silicon of the CPU core itself. It's on a separate chip. But it's on the same motherboard, so it's not somewhere else. And so accessing the main memory takes you, 3 minutes and 20 seconds, and sending data across the network takes 5 hours and 33 minutes and 20 seconds, and so on. So these are large numbers. Of course, it's not that it takes days, but getting an understanding of the differences and how much time something takes between L1 cache, L2 cache, L3 cache, main memory, hard drive, network, you begin to understand very quickly that most of our troubles from a performance standpoint, especially these days, given that we access a lot of services and database, that if we could clean up that access and improve the performance there, we will see vast improvements of performance throughout our application, rather than focusing on the nano, micro, and milliseconds. Right? So I just want to preface that. Okay, so now let's look at some of the hardware here. Now over here you can see there's a, hopefully my mouse is being captured. Last few times my mouse has not been captured, so I'm hoping the mouse is captured here. The CPU core. So this is a sample architecture for the CPU that I have on my machine. Every CPU is designed differently, and I'll explain what I mean by that. And so it may not represent, whatever you might have on your machine or what you might be running on your servers, but this is how it is. So the CPU core has its own, in this specific architecture, this CPU core has its own L1 cache, and the CPU core has its own instruction cache, and then the CPU core also has its own L2 cache, which is not normal. As in, it doesn't have to be that way. In some cases, some CPUs, the L2 cache may be shared, which means instead of a gap here, all of this is L2 cache, and then these two CPUs here have the independent L1 caches, but their L2 cache is shared, meaning it's not independent like this. And that's the more common architecture. And then the L3 cache is shared across all 4 CPUs. This architecture is called the NUMA architecture, N-U-M-A, non-uniform memory access. The NUMA architecture. So it's important to even understand to some extent, like, what is the NUMA architecture of your CPU, or maybe the server CPU, server on which you're running your applications. Because that is also going to make a difference. And of course, the better the architecture, by better I mean the more L1 cache it has, the more L2 cache it has, the more L3 cache it has, and the more independent caches, meaning no shared caches, the more expensive the CPU is going to get. And you'll see why by the end of this episode. So now, for the CPU to operate on any data, the data has to be in L1 cache of that CPU. However, for the data to be in L1 cache, it has to have been in L2 cache. And for the data to be in L2 cache, it has to be in L3 cache if your CPU has an L3 cache. Many CPUs don't, because it's expensive. The memory, L1 cache memory and L2 cache memory and L3 cache memory, if such a thing exists, L3 cache, is a very special memory. It's super fast. It's on the silicon chip, on the same CPU's silicon, and it's much more expensive. So these are not kinds of things that you will see whole lots of in terms of sizes. But as I said, so the more cache memory your CPU has, the more expensive it is going to be potentially, and the more levels of cache it has, L1, L2, L3, the more expensive it's going to be. So not all CPUs even have an L3 cache. But the idea I was trying to get across earlier was, for the data to exist in L1 cache, it has to have been in the L2 cache for that CPU, or that NUMA architecture, if you will. And if there's an L3 cache, it has to be in L3 cache, and it has to be in main memory. So it can't just appear in L1 directly, right? Now keep this in mind. This is going to come and play a role in further discussions here, where any data that's in L1 cache has to be in L2 and L3. In this specific case, we just talk about this architecture throughout this conversation, and has to have been in main memory. And for the CPU to operate on it, that data has to be in L1 cache. So it can't just start working on something that's in main memory directly. It has to be in L1 cache. All right. Which is why the access speeds of L1 access to L2 access, main memory, and so on is important, because you'll see why that is the case. Now, the modern CPU architectures are extremely complicated. Well, probably complicated for you and me, I'm sure. Like the people at Intel and AMD think, oh yeah, no, that's really cool. It's difficult to wrap your head around all the things that are occurring in parallel that the hardware is doing for you on your behalf, because all is happening simultaneously. So it's happening all together at the hardware level, not at the software level. And the hardware is almost like there's so much of bandwidth on the hardware side, though they've stuffed so many things that the hardware can do simultaneously, that the hardware is assisting by doing a bunch of things in parallel or simultaneously while it's trying to execute your application. And the reason it's got so much of bandwidth is because our application requires data, and the way we write code is not the most optimal and so on. So the CPU core is just sort of sitting there twiddling its thumbs, and so it's got a lot of bandwidth. Essentially, in this case, the CPU is a 3.3 gigahertz CPU. There's so many cycles per second, right? 4 instructions per cycle is the typical that the CPU can perform. However, it's not that every instruction takes, or it can actually do 4 instructions per cycle. It's because it's doing a few things that we're going to be talking about today, further on from here. That is why it can actually do approximately 4 instructions per cycle. But that's not normal. An instruction can take 3 to 4 cycles. A standard x86 instruction can take 3, 4, 5, and even more number of cycles, CPU cycles. But these modern CPU architectures are superscalar architectures. So they're doing multiple things simultaneously, and the net result of all of that is that you're effectively performing 3 to 4 instructions per cycle. And that's what I mean by the hardware is doing a whole bunch of things to try and make that happen. So one of the things it's trying to do is make the instructions pipeline. The instructions have a cache. The instructions have a pipeline. The data has a cache. As you can see here, there's an instructions cache and a data cache. L1 is the data cache, and the instructions cache is the one that's called instructions cache. Each of them have a cache. And the instructions pipeline is working ahead. So maybe it's executing instruction 1, but it's looking at instruction 2 and 3 and 4, and it's trying to start working on those instructions and trying to hopefully process the instructions and be ready for when you need the data, if that's possible. So there may be some instructions that are dependent on the previous instructions, success or previous instructions, branching, conditional statement. But there are many other instructions that can just be executed. We're just waiting for it. So the instruction pipeline is actually building up this pipeline. I think it's about 7 instructions. And it's starting to, different hardware is different. It's starting to try and process these instructions ahead of time, and it's predicting at the same time. It's crazy. We'll talk about branch prediction, but basically the CPU is predicting, let's say, as an instruction, the branch instruction, the last time this branch went this way, so I'm going to assume this time also is going to go this way. By this way, I mean true or false. And then based on that, is processing a few instructions in the pipeline. It's doing all these things simultaneously while the actual instruction, it is what you would call your instruction, is executing. Such that as soon as this instruction is executed, it has a bunch of other instructions it could potentially execute in every cycle. So in every cycle, it's trying to process these 3 or 4 instruction sets. That's extremely complicated to kind of wrap your head around, but of course, luckily we don't have to worry about this. This is all being done at the hardware level. It's an optimization that Intel and others have come up with, and they guarantee that things are going to work the way we expect. We have to just worry about writing the code correctly. But there's such a thing as an instructions cache, and that is doing this thinking ahead kind of thing. So the next thing is the prefetcher. Now, your code while it's executing requires data, and let's say you're in a for loop, just to keep things simple. As you're iterating over the for loop, you have to go get the next piece of data, the next piece of data, the next piece of data. Maybe that data is not in L1 cache. The prefetcher is predicting, is anticipating, is speculating that you're going to need that next chunk of data pretty quick. And so it actually is going and prefetching that data. Now it could be wrong. It could misfire, if you will. But what if it's right? It's just saved us a whole bunch of CPU cycles trying to fetch that data from main memory. So, and bring it into L3, L2, L1 cache. So the prefetcher is working ahead, understanding all the other predictions that are being made by the hardware in terms of the instructions pipeline and things. And then based on all of that, it is going and prefetching data if it can predict what is going to be required next, and then it'll go and do that. This is all at hardware level, by the way. This is not happening in software. right? This is all happening at hardware level. And luckily, we don't have to worry about all this jiggling and juggling that's going on at the hardware level. So the prefetcher's job is to prefetch data and instructions, by the way, because it's also, depending on your branch, you have to get a different set of instructions. So it's doing kind of both. There's an instruction prefetcher as well as a prefetcher for data. All right, are you with me still? All right, let's look at the next idea. And then we have the branch actually, you know what? I've got a few slides seem to have zipped by. Oh, there it is. Okay. The branch predictor. This is an interesting one. And I can explain this through an example code, if you will. So let's say you have a collection of something. Let's say you got 1 million things. I don't know, customers, whatever. And you're iterating over these customers over a loop. And let's say, to keep it simple, inside of the loop you have a condition that says, well, if the customer is from Virginia, then do this, else do that, let's say, simplistically. If amongst those 1 million customers, if the customers were not sorted by the state, in this case because you're using that conditional on a state, if the customers were not sorted, the branch predictor will potentially be misfiring, if you will. It'll be miscalculating. It will not be able to predict. It'll be a miss versus a hit, as we call it. It'll be hit versus a miss very often, because it can't. There's no prediction. It's random. The data is your data is random. The collection of customers are not sorted by state, and so the branch prediction can't necessarily help. Now, if you sorted your customers by state in this specific case, because we are pivoting around state and inside of the for loop, then the branch predictor will predict. Because, by the way, none of this is using AI of any sort. Maybe in the future they will, but this is not AI based kind of predictions, but this is just predicting based on previous happenings, if you will. So if the first time when you went through the loop, it went down, let's say, the left branch, it's going to predict, okay, maybe the next one is also going to be left one. It goes down the left one and the left one. And so basically it's going to keep going down this path. It's always predicting, which means it can then continue to look ahead. That branch prediction, when it succeeds, it's already looking ahead. Based on that prediction, it's saying, okay, I'm predicting it's going to go down this path. Therefore, I need to get that instruction into my cache. Therefore, I need this data ahead of time. And so it's doing all of that work up front, 3, 4, 7 steps or so ahead. But if it misses, then all that work was lost. And now you can't even process so many instructions per cycle, because all the instructions that were processed have to be thrown away. So it has to sort of back up and start from scratch and go down this path. And so you will find that typically if you sorted data, there's many things you can do, by the way, in C#, that you should do if you have to work at that level, where maybe sorting the data ahead of time and then processing the data might actually be much faster, because the branch predictor can actually help you. And there are a few other things, but let's keep this example in mind, and then I'll try and use the same example to give you different ideas to what you can do as we go past the different things. Now, I'll skip this slide. It's not so relevant for what I'm trying to get across here. Let's imagine we were trying to visit every element in a matrix, and there's 2 ways to do it. We can do it as row major, meaning row by row by row, like that. Like I think is like the normal for most of us. We kind of think this way, left, right. Or you can have column majors. You basically go down this way, right? Now it turns out that the code is not any different. It's either you're going, this way or this way. So the code you write is not any different. It's not really complicated code. But it turns out that this code, the row major, will outperform the column major, no matter what the language is, no matter what the platform, the hardware is. It is always going to outperform. And there are quite a few reasons for that. So we need to understand that. And you can see that in the column major, there seem to be these kind of jumps. That is almost linear, then it jumps again, then it's almost linear again. So these jumps are not coming because of some glitch these jumps actually indicate to you your hardware in many ways. In other words, there was data, let's say, just as an example here, that first jump was because the data was not in L1 cache, so it had to go and get it from L2 cache, so it took a little longer. Now that it's come back from L2 cache into L1 cache, it kind of becomes linear again. And then it has to jump again to go to L3 cache and so on. So these jumps are indicating something, because depending on the data and the size of the data, all these things could change. But those are not glitches. Those actually will happen even, for other cases, because of the hardware's shape, if you will, the NUMA architecture, as well as the size of caches, the L1, L2, and so on. All right. So, cache lines. So next up I want to talk about cache lines, because this is what the reason for why the column major the row major versus the column major was faster. The CPU, of course, as I said, the CPU requires data to be in L1 cache for it to work on that data. It can't work on data that's in L2 cache. It has to bring it from L2 cache to L1 cache to work on it, and so on. So now let's say it goes, the cache line is the smallest amount of chunk of data. It's a unit of data, if you will, for the caches. So when you go and read data from the cache, it can read that chunk. It can't read less than chunk, and it doesn't read more than the chunk. If it has to read more than chunk, it'll come back and read the data twice, meaning once it'll get this chunk, then it'll get the next one. So that's like the unit, if you will, for the CPU with regards to its cache line size. And then the caches are kind of designed around that cache line size. Now, if the CPU has to go to main memory to fetch the data because it's not there in L1, it's not there in L2, it's not there in L3, it has to go to main memory, it's going to read cache line sizes of data in chunks. So imagine you're going to the grocery store, and so you being your wife or whoever, your better half, the person that's running the household, sends you off to the store saying, get me milk. And so you've taken off from the core, from your house, and you're going over to the grocery store, and that's a long trip. And then you get to the grocery store and you go to get this milk, and of course there's a specific brand you want for this milk, let's say. The CPU, when it goes to that store, is going to grab all the milk, no matter what the brand is. It's just going to get the whole chunk. It's going to put it on like that on all the milk bottles and put them back in the bag and bring them back to the L2, L3, L2, L1 cache. It can't pick and choose the data, so it's still stuck in that cache line size of data. So imagine an array of data, our matrix from the previous slide. If you went row major, it would pick up chunks at a time, and the predictor will be predicting also that you want the next cache line, the next cache line, the next cache line. So the predictor is working ahead, you're working in the same order in which the branch prediction will occur, and the prefetcher is going to be prefetching that data from the main memory also, because it's predicting the next piece of data you might need. And the funny thing is, let's say for every cache line you can do 4 iterations, just as an example in your loop. Then for 4 iterations you don't have to go get the data. But because you're going in row major, the prefetcher and the predictor are all working towards that same thing, and they say, okay, it looks like I can go get the next data ahead of time before you even need it, because I know I can see from your actions that you're going to need the next cache line. And so everything is kind of working perfectly because your software is written for the hardware, if you will, right? And assuming that the data structure is an array and it's not like a hash table. The array data structure is the most favored data structure when it comes to this kind of work at this level, because of the fact that arrays are contiguous in memory. And of course, as you've learned recently, that the data CPU gets data or fetches data cache line sizes at a time, and if it's all contiguous, every time it reads the next cache line, the data you want is also in the next cache line. So it all sort of works out, right? Most people, when they have performance issues, will say, okay, your problem is you're not using an array. Literally, it works out like that. So anyway, I'm hoping this the prefetcher, the branch predictor, the cache lines thing is sort of making sense. Keep in mind that the CPU always has to get one cache line at a time, And when it reads from L1 cache, or it reads from L2 cache, or reads from L3 cache, it's reading a cached line at a time. Even though it might be reading just one byte from the cache line, it's reading the entire cache line. It's modifying the entire cache line, or it marks that. If you were to write to the cache line in the CPU, so you're modifying your data, then when it touches that cache line to modify even one byte in the cache line, the entire cache line is considered invalidated or dirty. And that becomes important for another topic we'll talk about later, very soon. So keep in mind that the cache lines in this specific CPU architecture is 64 bytes long. And so chunks of 64 bytes can be read. And you know, when you go to the grocery store, you can get 64 different bottles of milk. But it's a visual you want to have. It takes a long time for the CPU to go to the main memory, and if you don't do your shopping, if you don't keep all the stuff you want to buy in one aisle and all together, then it's going to take a lot of time for you to go pick up all the things that you need. But except in your case, when we go to the store, we make one trip to the store and we go about picking all the things we want. But think of it this way: you can only go to one place at a time in the store, and you have to go back home and come back each time. That's what the CPU is doing. It can only pick up cache lines at a time. So even though it picks up an entire cache, let's say in the example of the milk, of all the milk it brought back, you just need the one bottle, right? The rest of it is a throwaway. So it's just going to throw it away because you're saying, okay, the next bottle of milk is, this thing, and that's in another cache line. So it is going to be making multiple trips. So if it's an array data structure, it's all going to be in contiguous chunks of memory, and the contiguous chunks of memory include the data that you will require. And so the prefetcher is prefetching with the prediction, and when it prefetches the next cache line, is exactly the data you require, and so it all sort of works out. So we talked about the branch predictor. We talked about the instructions pipeline. We talked about the prefetcher. The prefetchers for both for instructions as well as for data. The branch prediction. Now, what is a branch in CPUs? Is even a for loop actually is a branch. I mean, we might think of it as a for loop, but essentially it's a branch. In assembler, you go step, and then you say, go back here. That's considered a branch. So even a for loop is a branch. And for loops, of course, very easy to predict because it's always going to go back here. It's always going to go back here. Or it maybe because you got a condition in the statement, it'll boot out. But for the most part, that's a very simple prediction to make. The predictions that I'm talking about are within the for loop if you have a conditional statement, and you have a condition based on something else. Now, in line with the cache lines discussion, let's say I have this data structure, this customer that we've been looping over is massive in terms of the number of attributes that this customer has. Let's say it's got 400 attributes, not very uncommon. And you're iterating over these customers, and you're interested only in 5 of those properties: the state, and let's say the email address and something else, right? Let's say you're only interested in that data. You seeing where I'm going with this? If your data structure was tuned for the work you're doing, right? So if you got a cache line, and let's say our data structure, the customer, so we got 64 byte cache lines, and let's say we had our data structure was 256 bytes, of which the data we required was kind of spaced in such a way that is in every cache line there's only one piece of data because 64 bytes, so on. Then you would have to read the cache line 4 times just to process this one iteration, if you will. Because your data structure is so big and there's so much of waste of data in between the data you actually want. What if, before starting this processing, you copied the data into a smaller structure that had exactly the information you required in order to process this thing? And that's in an array. And then you iterate over this loop. Things can go faster. Now, I'm not saying they're guaranteed to go faster. Nothing in performance is guaranteed. You have to benchmark before and after. Make sure you make one change and test again, and make one change and test again, so you know which changes are giving you a positive change and which changes that are maybe not having an impact or they have a negative impact, right? Nothing in performance can be assumed just because I know how it works. So it's going to be faster. Even I don't never do that. Never make that assumption. I have a hypothesis, but it has to be proven by writing some benchmarks and baselines and stuff like that. All right. But I'm trying to make you understand, or trying to help you understand the cache line idea, that to fetch a single customer, if that customer were so big that it occupied more than 64 bytes, then it can't even fetch a single customer in one cache read, in one main memory read. It has to make 2 trips now to get that one customer. And then you're iterating over 1 million of those. And then for every one customer, you're going, 2 times. And the other flip side of that is if your data structure was small enough such that it fit, more than one of them fit into your 64 bytes, right? Then by going to the grocery store once, you got your data you want, rather than having to go once per iteration, right? So all the data structure, the data structure in terms of the kind of data structure you choose, whether it's an array or a hash table or a binary search tree or whatever the case may be, and the size of the data that you're working on matters because of the cache lines and the amount of data that has to be shunted between L1, L2, and L3 cache and so on. So all of this is going to make a difference. Now, there's another idea. There's 2 ideas I still want to talk about. One is called memory coherency, and the other one is called fault sharing. They're both actually very related ideas. So I'm going to talk on the screen here. Talk to the screen here. Let's say on this core, I'm working on some data that's in L1 cache, but you know that for the data to be in L1 cache, it had to have been in L2 cache, it had to have been in L3 cache, and it has to have been in main memory. So if I'm working on something in L1 cache, then it is also there in L2 cache, and it's also there in L3 cache. All right. Now let's say that on the other core next to it, I'm parallelizing my workload, so I've sort of split up the data, and I'm working on, like 2 different sort of parts of data, hoping that there'll be no collisions. And let's say, as an example, both of these cores are working on the same cache, the data in the same cache line. They're both working on the data in the same cache line. As far as they're concerned, it's in their L1 caches, so it's not like the cores are confused about where the data is. And luckily for us, as software people, we don't have to worry about this hardware issue or this hardware thing I'm going to talk about. But see, it's important to understand that's what's happening. Let's say core 1, the one over here, modifies that data on that cache line. The moment it does that same cache line in L2 cache and in L3 cache and memory has to have been invalidated, has to have been marked as dirty. And now the other core wants to read that data. What's going to happen? So as I said, luckily we don't have to worry about that. That's not an issue that we have to deal with on the software side. On the software side, we do have to deal with making sure that if something is writing to a piece of data, then nothing else can be reading from it. And conversely, if something is reading from the data, then you might have to block the writers until the reading is finished, and then allow the writers to write the data. And there's all kinds of ways to do that in software, like mutexes, semaphores, and what have you, as part of the primitives for locking, synchronizing access to memory locations. So on the software side, we have to make sure we do our part in that sense. But on the hardware side, this sort of thing can happen where 2 cores are potentially working on the same cache line. Maybe it may not be the same data on the same cache line, but certainly on the same cache line, because the CPU will invalidate the entire cache line if one core writes to one cache line. Then that cache line is dirty for all cores. And everyone needs to be told. Every core needs to be told that cache line is dirty, and the hardware has to go through, some effort to synchronize all that data. Now that core 1 has modified the data, is to synchronize that same data and make sure that all the other cores are seeing in their cache lines the same data with the same new value. Right? That doesn't come for free. It costs us some amount of money. Well, maybe it costs money to some amount of CPU cycles, but it's not cheap, the amount of CPU cycles. But it's not something we have to worry about, luckily. But you have to keep this in mind. This could also be happening, right? If your processes, your parallel processes are such that they're potentially on the same cache, working on the same cache line, well, one modifying something that was trying to read it, or maybe both of them are trying to modify two different things on the same cache line, that's just going to cause a lot of other slowdown. And if you rethink your strategy a little bit, then you could speed things up. And so we've gone through the instructions pipeline, we've gone through the prefetcher, we've gone through the caches and the cache lines. We've gone through the branch predictor, and this other, the last concept that I was talking about is called memory coherency, and the fact that the two CPUs seem to be sharing the same data even though they're not. That's called false sharing. So false sharing is this idea where they are on the same cache line. Two cores are operating on data on the same cache line. They're not operating on the same data, but the data happens to be on the same cache line. And now because one of the cores happened to write something to its data on the cache line, all of that, where all the copies of that cache line across all the different L1 caches, let's say, and L2 caches, have to be invalidated and synced up with the new values. And so it's a false sharing, because even though you're not sharing across CPUs, the fact that they're feeding the impact, it's false sharing. Oh, all right. You're still here, still survived it. I hope this has not been too fast, but at the same time, it's not been too deep as well. I think I'm hoping to have hit kind of that sweet spot where conceptually things make sense with the help of some C# examples for how things might work, or how you might be able to reason about your code in the future with regards to branch prediction, in regards to cache lines. Data structures make a difference. Essentially, if you are passionate about the performance of your code, it is imperative for you to think about the data structures you use, whether it's an array or like a binary tree. And of course, binary trees are pointers. Like this, one pointer chase another pointer, chase another pointer, and it's just a pointer chasing thing. And dereferencing every pointer could be like 100 CPU cycles. And do you want to spend that time doing that, or do you want to have an array structure? So it depends on what it is. But if you have to consider the data structure you use. You have to consider caching, what we talked about just now, and memory, and access to main memory versus having it in cache, and so on and so forth. The whole notion of trying to think about performance without knowing or understanding any of this stuff is doesn't make sense. Cache lines are key. Understanding the fact that data access or memory access is done by at these units of cache lines, if you will, is key, because that might make you think about the data structure. Like, do I want to iterate over 1 million clients, customers, where each customer, the data structure is so massive that it spans 15, 16 cache lines? Or should I copy all that data into a smaller data structure that's just enough data that I need, and I can iterate over that data structure, and then that'll be a whole lot faster, right? So again, please try and baseline and benchmark and that sort of thing. I hope this was enjoyable. I love this topic, and I hope I was able to explain things in a way that you understand it, and I shall see you next time.